Ta-da! Welcome. Thanks for joining so late today. I know that some already left, so some people said you want to join but couldn't. We want to talk about parallel programming today and why synchronization is needed and it's not what you think. So what's in for you and why you should stick around. We want to learn about some of the computers and compilers optimization that makes concurrency in your code so hard, and it makes actually your code really, really fast. We want to learn about basic language concepts and some hardware concepts. And at the end of the day, I want to create awareness for common programming mistakes when talking about concurrency. Just to make one thing clear, I'm not an OpenGDK developer, so everything you see here is just from other slides, from other talks and things like that. So it's just summed up information. I validated, so I tried all of this myself. And of course, I live by these rules, and so far I live quite successfully by these rules, so they must be right. You will see code, even assembler code. If this doesn't scare you, great, then let's continue. So my name is René Schwietzke. I spare you the complicated surname somehow. I'm one of the co-founders and managing directors of Acceptance. We do software testing for a living. We have our own load test tool based on Java. That's the reason why I know so much about Java. I'm probably maybe the only one here in the room who started with Java 1.0. Who started with Java 1.0? Yeah, I know. OK, good. And I'm also a performance tester, and you have my social thingies there if you want to follow me or just send me something. OK, first, motivation. This is Java in perspective to all of the other languages in terms of time, memory, energy, time, and things like that. This is officially benchmarked, available on the internet. You see the link there. Java is one of the top languages. It's basically one of the languages that's just very close to a machine-compiled language such as Go or Rust or C or C++. So Java is insanely fast and efficient, even so you might not think that Java is the most efficient one. But if you can select languages, Java is very close to the top tier. And there's another motivation. And nowadays, we have basically our huge multi-core machines. You might have one of these newer Macs with an insane amount of CPUs, 2 different CPU types, by the way. We do multi-threading all the time. And people say, we must be efficient. Efficient means don't burn too many machines, don't rev up the CPU too much. Cost is important, and maybe the environmental impact is important as well. And we know that concurrency is something you can barely test. If you have written a unit test that should prove that your code is safe in the sense of concurrency, it's likely incorrect. It might prove that your code works, but it's probably not proving that it's really safe. And also Java is older, 1.0. And in this case, it's a language that's very close to C. It has been modeled after C, so you are very close to the machine. You're very close to some details of what you can do with the language. All the newer ones like Go and Rust and Kotlin, they abstract a lot of these things away, so you're not exposed to it. But if you're exposed to it, you can do a lot of things to make your code really run fast and scale well. If you're a low-level compiler developer, a low-level library developer, you have to know all of this to make your code really, really fly. So there are certain misconceptions in the room. Most people think the code they see is the code that runs, and I will show you that this is absolutely wrong. Synchronization is only needed if you do some transactional stuff within your code. So basically only one guy can do the famous, there's a bank account, I withdraw money, I add money to it. Just to make this safe and cool, I need a synchronized statement. If I add another CPU, things get way faster. That's not really true. And you can debug and profile everything, which is also not true. And memory, you have plenty of memory, and it's very affordable, which is not true. And at the end of the day, thread contention is the only problem we have when we talk about concurrency. OK, as I said before, some of the stuff is taken from others, because I learned from Doug Hawkins. He was here on maybe this stage 2017 and talked about concurrency concepts in Java. I will use some examples from him. And there's Alexei. Alexei lives in Potsdam in Germany. He works for Amazon and is part of the OpenGDK Corretto team. And he does really, really deep-level shit in the OpenGDK. If you follow his blog and what he posts, really, really good details about how the GDK works. OK, let's summarize the entire thing that's coming in 3 slides in case you have to leave soon. First of all, no spec, no fun. Java has a specification called the Java language specification. Did anyone read the Java language specification? 1, 2, OK, 3 arms maybe? Especially chapter 17. No? OK. It defines the Java memory model. And Java was one of the first languages, or the first language, to really come up with a specification before developing anything. And the Java memory model defines basically how Java runs in conjunction with your memory, with your RAM. It defines how the correctness is handled in terms of state and memory. And so, just in case, Java does this thing as if there's one thread unless you tell me otherwise. That's the golden rule of the VM. If you don't tell me anything, I assume there's one thread, and what I do is I just run it, and the result at the end is important. Nothing in between, I don't care. The final result is important. I will do everything I can to make this run fast, and the result at the end will be what you expect. Nothing in between. Java builds up single-thread consistency. And we see later on a lot of examples that basically makes your head spin. The compiler doesn't prevent us from doing crazy things in Java, sadly, but due to the age, certain things can't be changed anymore. And if you say, run 2 threads, well, if you're running 2 threads, you don't tell Java anything about what you would like to do in terms of communication between these 2 threads. So you have to do this explicitly. Java always says, each thread is a single one. Just deal with all the things I see as it would be a single one. At the end of the day, the result is what counts. And because I started with Java 1.0, I can tell stories. And one of the stories is we once had a transition from Java 1.4 to 1.5. And the GLS was changed. The language model was adjusted, and especially around the memory model, how to handle things. And a lot of large programs stopped working. They were just getting into spinning loops and stuff like that. Because before, by accident, there was no need to synchronize anything. Now, with 1.5, which scaled way better on multi-cores, Java did what the spec said, and now your code was broken, because you incorrectly synchronized things in the first place. To be honest, they haven't synchronized anything, but it just worked. OK, then we're done here for the first 3 slides. That's what you have to take home. Now the details, if you want to stick with me. Memory is everything, seen from the Java point of view and from the computer's point of view. Left side, this is what you see as a Java developer. There's a thread. There's a stack attached to the thread. This is something you don't even see, but you might know that this is there, because you might have seen out-of-stack exceptions, something like that. And there's the famous heap, the huge memory blob that somehow rules the world. On the right side, you see how a computer looks like. It's very simplified, to be honest. You have some cores. Each core has registers, the smallest memory piece you can get. You have caches, L1, L2, L4. L4 is, by the way, one of the caches in one of the new Intel architectures. And then there's virtual memory. It's not real memory. That's a combination of disk, some swap space, and some other things, and the physical memory you know. So where do we live? And it's actually quite readable. This is an example. Most of the things, you can't see where they live. They're just there. So the type doesn't indicate storage or any kind of sharing. If you have something that's kind of local, you don't know if this is local or if this is public, but just in your local scope. there's a simple rule. If you can synchronize on something, it can and could be shared. So any object you can synchronize on is something that could be shared, maybe by accident. There is Valhalla coming up. I don't know if you joined the talk yesterday. Valhalla will change not really the Java memory model, but how some objects are built. They're no longer objects, they're basically lightweight. So it looks like a class, it feels like a class, but it's an int. And you can't synchronize on these objects anymore, hence, you can't share them. So the golden rule still applies. That basically means if there's something immutable, you can't change it, it will be probably safe. And if you cannot change it, you cannot screw it up. Almost. There is one thing I will tell you later on where immutability is not immutable, and you don't even have to do reflections for that. Okay. Sharing in data arrays. I haven't defined some of the terms yet, so let's talk about sharing. When one other thread can see or change data that someone else created or owns, that's sharing. And the most important thing, and most people get this wrong, it doesn't have to be at the same time. It could be that there are minutes, or not really hours, but minutes in between these activities. So one thread writes something and the other thread wants to read this a minute later. You can have a data race. The other guy might not see what you have done before. Typically, when you say, hey, concurrency, we just talk about one thread doing exactly at the same time what another thread is doing, so we want to prevent this. That's not true. What we have here is a problem that's about consistency of the memory. And there's a data race definition by Oracle from one of the other projects that says basically one or more threads in a single process access the same memory location concurrently, and at least one of the guys accessing it is writing. Then you get basically into data race problems. Okay, concurrency. What is concurrency? Concurrency means that data is accessed by two or more threads. At least one is writing. And there's no time definition, as mentioned before. So nowadays, concurrency is not longer that the thing is done at the same time. It's just that, it happens that we share data and we do writing and reading on it. That's it. It can be minutes apart. So let's look behind the scenes and see some examples why this is so important. This is readable. This is a shared int, maybe in an object. Is this an indivisible atomic operation? Yes or no? No. Why not? Okay. This is the bytecode for it. And this is basically how it would look like if you translate the bytecode from a stack machine into a register machine. And this is the assembler code. First 3 lines is typically assembler code, reading from memory, incrementing, writing to memory, because on most machines you have to put something in the register if you want to do something with it. In the Intel world, you have also this last line, which is barely used. You can directly increment memory. You see this occasionally if you look into your compiled Java code, but not often. This is the local version where we do a +2. Atomic or not? No? Okay. That's the bytecode. It's really short. And this is the assembler code. So we move something into a register, which is the 2. And because our local is already in the register, we just basically add it up. So it's 2 instructions. And this was kind of a trick question, because everything that's local is by definition safe. And in this sense, not really atomic, but it can't be divided by someone else. So nobody can go in between these 2 instructions and do something with it and see some states. It's basically safe. So we have a new statement. And so the last line, point shared, means new point of x and y. Is this atomic and is this safe? It's not safe, not atomic? Okay. Well, if you translate this into some pseudocode, it might look like this. So we have to get us memory, then we initialize the object. There is basically inheritance from objects, so we initialize this piece, and then we assign the two variables with their values, and then we publish the information. It looks like indivisible in the sense of nobody can get in between and see a state that's not cool. Actually, it is. So it's one of the most dangerous things you can do. It's not an immutable object, even though you think it is. And in about 20 slides, we will have learned why. Next thing is visibility. Java gives you one clear guarantee. And if you compare this to C, it's relatively nice to know, is you never see garbage in your memory. So if you say new array of int, it's all zeros. If you say new array of object, whatever, it's all null. If you basically say, hey, declare an int, y, and you don't say anything, it will be 0. So there's never garbage at all. So the spec says you see never garbage. And this is done by writing to a variable first, or to the memory location, and then you can read from it. So Java guarantees that someone has written to this position before you actually read for the first time. This is a very strong guarantee, and really makes clear that you don't see any garbage. If you go to, let's say, your operating system and say, give me a gigabyte of memory, it will be just garbage. And the operating system, at the end of the day, won't even give you real memory. In the first place, it just says, you know, I have it. And only if you access the memory, it will be basically really provided to you. Before, I just get, yeah, you know, it's there. That's the difference. In Java, it's kind of, it's there. It's really allocated. This really has been written to. And there's a problem. If you want to write something that's really, really fast, this is a problem. Because if you say, give me a kilobyte of int array, we will write to it first. Java will do this for me. And then I will initialize it with whatever values I want. So we have to write twice to it, even so the first one doesn't make any sense because I'm writing to it anyway. So this is a performance penalty at the end of the day you can't avoid. Of course, you could really do nasty things, but we don't want to do this. So this is one of the problems. So if you ask for memory, someone has touched it before. In this case, it's the Java virtual machine. Hence, Java has a limited memory throughput when you allocate new things. It's not about allocating and being happy with it. It's you allocate, someone writes to it, and then you get the memory. And then you write to it, so it's basically twice the amount of writes, which is kind of a little inconvenient. Not everything will be visible. So if we do this, we have a shared variable, like let's say an int, and we want to write 20, 40, and then we want to print it. Java builds a dependency graph. And it will build this dependency graph mostly when it JIT compiles the code. Might not do this in the first place, but when it does a C2 compilation, so the final one, it might just do this and say, you know, let me look at this and say, single thread consistency is what I guarantee, so let me rewrite this code. And the 20 is dropped. You will never see the state 20 in the memory at all, because single thread consistency says, I don't have to. You can even do other things like, you know, print 40 instead of print shared, and you're good. Not everything will be stored. Same story, because it's very efficient to write all the time through memory. Java will actually create a local variable, which is a register, and then we just basically use this for calculation and summing up, and then later on we write the state back. You don't see this in your code, but it will be done. Can this be ever 30? A square of a number, can this be 30? Yes, no, maybe? Okay, I'll take this as a maybe. This is what a compiler does. It basically has two locals, and then it just basically does the multiplication. The problem is if we have thread 1 and 2, and it's a shared variable, the first one might write 5, and the second one might read this, and then the next one does 6, and the next one reads this, and then basically the square of 5 is 30. This is the reality, by the way, and this is the reason why testing concurrency is really hard, because the compiler says, why should I read this memory piece twice? Let me be a little bit more efficient. I read it once and multiply it. And you will get by accident, this is the real code, by accident you will get basically your desired 25 or 36, whatever, never 30, but this is by accident, because the compiler decided to do something to optimize your code. It's not a guarantee that this will ever work. If the compiler builders decide to change this, you might be screwed tomorrow. We can also do other things like reordering. So if we run this code, we just build this dependency chart and see, shared Y, nobody uses this at all. But of course, it's shared. I have to initialize it to a certain extent. Let me rewrite the code. And this is absolutely legal because we are running single-thread consistency. This is also legal. So we can do all these optimizations as long as the end result is the same, not any intermediate result. We don't care, or Java doesn't care, we might. And this is what happens. This is also legal. It's stupid code, but it's legal. So the GLS states, to some programmers, this behavior might seem broken. However, it should be noted that this code is improperly synchronized. And so the semantics of the Java and the computer allows you to basically see garbage, even though you think your code is cool and safe. And let's detour to modern machines. These are the levels, basically, of the CPU as well as the world. Talk microservices, for instance. If we assume that we have a 3 GHz CPU, it's 0.4 nanoseconds for a single cycle. If we have to go to the L1 cache, it's 0.9. And nanoseconds are kind of inconvenient. Just let's turn this into seconds. So if one cycle would be a second, and then we have to go to main memory, it's about 4 minutes. So it takes about 4 minutes for the CPU to get something from main memory. If you go to your hard disk or to NVM, it's 17 hours. Just keep this in your head when you program the difference between a CPU and what really happens if you give the CPU a human life and use seconds. So it's really expensive to go to memory. Hence, we don't want to go to memory. So the compiler does everything necessary to avoid going to memory. And for whatever reason, this is a little large. Here we go. This is a modern CPU. It's not the most modern one. It's a KB Lake, but it's one of the modern ones. They have 5 stages, 6 stages. So they basically take the instructions, they decompile them, make micro instructions out of them, and then they have to fetch memory and stuff like that. But the most important is the green one in the middle. They have several execution units. So to be efficient and use everything they can do most efficiently, they can run 4 to 8 instructions at the same time. So you have seen, for instance, 3 instructions beginning assembler code. This might be just 1 clock cycle on the CPU, if possible. So if we turn this into something we can digest as a human, the left example is the stupid transactions of money. And of course, you never should use double for money representation, just in case someone wants to program this example at home. And then we have some pseudo assembler code. We move stuff into a register, and then we do multiplications and additions. If we give this to the CPU, it will look like that. So we have 4 execution units, and we can basically take apart our code we had before and run this on different units at the same time. So these 9 instructions in the beginning turned into 5 cycles because I can run them in parallel. And so I do about 1.8 instructions per second. This, by the way, is an efficiency measurement. So you get concurrent code automatically. You don't have to do a thing. This is what the CPU does for you. And there's also one thing that's called the fortune teller, or branch prediction in the CPU. The problem is we have these dependencies. We want to fill our execution pipeline. We want to fill our execution units. The problem is if I run into an if, I don't know which branch will be next. So I have to wait till I have the result, which basically means all the other execution units have to wait. And I have to maybe do all the decoding again I already did, and prefetching of memory or whatever. So the CPU will speculate and assume most of the time it was branch A. Let me go branch A, do this already, If it was a miss, so we take branch B, throw away everything, restart the process, and do branch B. So this example here has two sorts, a sorted array and a reversed array, or an unsorted array. By the way, I just modified the example a couple of minutes ago. It's not reversed, it's unsorted. Sorry about this. So if we run this code, which one will be faster, just by summing up things here, and how fast, or how much faster? Give me numbers, please. Huh? Pardon? 10 times faster. That's a number. So we run it, and it's 4.7 times faster, but close enough. So our sorted part is faster, and now the question is why? And we can just turn on some profiling tools on the CPU, and we see in line 4 that for the sorted one, we had just 6 branch misses. And we did about 17,800 branches. And for the unsorted one, we had 1,000 branch misses, and we did also 17,000 branches. So the prediction which branch to take failed. And here you can see the efficiency measurement, instructions per clock, IPCs. The first one, 3.9, so we get basically a pretty good filled execution unit, because all the units we have, 4 to 6, 4 to 8, are filled. And the other one is 0.75, not even one unit is fully filled, because the branch prediction failed. So the computer says, damn it, I have to change the code in a way that it's really efficient, or the compiler will do this, or the CPU will try everything necessary to make it efficient. So in this case, you can see something is running in parallel, and someone is already predicting which code to run, and it will run this code even so you never told your CPU this code has to be executed. So what we learned so far is the code you write is not the code that runs. It looks totally different, and it's already concurrent code. The compiler can modify your stuff. It can remove and add code. You might just not see a value written to a variable. It can reorder and speculate things, and it can run instructions in parallel. You probably think like a 1990s compiler when you read your code. Or you execute the code in your head like a 1980s computer. We all do this, because nobody does things in parallel. If you try to read your code, you read the code as you would interpret this as a human, which is wrong nowadays. This was okay in the 90s. This worked in the 90s. So we don't have time concurrency. We already talked about this. So we have the problem that we have to establish some kind of order. So we know that the order will be changed and something will be dropped. So we have to make clear that this is not the right thing to do. And we can establish a rule that's called happen before relation. So we tell our program code, this has to happen before that. And we have tools for that, and we'll get to these tools in a minute. So we introduce synchronization, and we can establish a happen before relationship. So let's get back to our new. We learned a lot about CPUs and GVMs and compilers. So the left one is incorrect immutable code. The right pseudocode is what maybe gets executed in our head. And now is the question, why do we see something else than Y and X? Nobody? Because code gets reordered. So the computer decides, or the CPU decides, or the compiler decides that the shared storage is expensive. So let's start this early. So I get me the object, I have the memory position, and I already write this reference to my variable. That's absolutely safe. And then I start to initialize my program code, or basically my variables. In between, Java writes 0 to it to basically guarantee no out-of-the-thin-air reads. If you just basically access the shared one now, you might see 0, basically a different value than you initially thought might be in your immutable object. So your immutable object is not immutable. It is immutable forever after the first couple of seconds. But in the beginning, it's not immutable. By accident. You, of course, haven't designed this way. And also this famous one, the double-track locking, if you want to create a singleton, you might have seen this code before. Someone said, synchronization is expensive, let's do this crazy trick. So instance, null, yeah, then go into a singleton synchronization block, and then check again, because someone else might have been in this block before, create a singleton, and return the instance. This is garbage code. It will work most of the time, but there are kind of moments where it totally fails. And it fails because of that. Because the code is basically writing the instance before it finished the initialization of your singleton object. So there is a moment where your object is basically garbage, but you can already work with it in a second thread. You have to do something about it. And this is basically what we can do. Fences to protect us. Or I think one famous comedian always said, silence or I will kill you. Or silence, I will synchronize you. So if we have no fences, this might happen. Left side, we have a producer, says share data, something, and then I say I'm done. And right side is the consumer. If done is basically not set, I spin and do something crazy. If ready, I will print it. Your computer, your compiler, your CPU turns this into shared done first, and then I initialize the data, and the right side basically says, I don't have to read the memory all the time. Let me create a local variable, which is false, which is true, because I read this after the left one has already said done. You just skip your loop, and you print something that has never been initialized. This happens a lot if your code is incorrectly synchronized. And this might not happen now, tomorrow, or the day after. It might probably happen at night, right before Christmas, when someone rebooted your production instance and decided you might need a bigger machine. So the CPU architecture basically is slightly faster, and then this will happen. You don't know why you have a null pointer exception in your code, why it doesn't run, why it doesn't start up. That's the reason. So fences are basically a way to tell the machine, keep the order. And so we introduce a fence in between shared and shared done to say, don't reorder. On the other side, we do the same. We say, don't do a local copy, always read from memory, and then we are safe. And the golden rule is what happens before the fence stays before the fence. What happens after the fence stays after the fence. Golden rule, nobody can play with that. The Java memory model and the CPUs guarantee that. You don't have to do this on your own. If you just introduce the fence, everything else will be done automatically. So what are these actions? Because we don't have fences in Java, at least not by name, of course we have something that is a fence. We have volatile, we have synchronized, we have a famous final, we have an atomic, and we have var handles. The last one I will skip for today. They can just fill it in another talk. And I think there was a var handle talk announced, I don't know. So each method can do different things, and you cannot just swap them out and say, okay, instead of synchronized, I will do a volatile. It's a complete different thing. Also, a final cannot be replaced easily with a volatile. So what can these actions, these fences do for us? We already know that the memory inconsistencies are our biggest problem. So we have a final, and the final guarantees, by the language spec, we only see one state. And this one state is basically the final value we attach to this object. So we don't see this intermediate one, the 0, because Java initializes everything. So final guarantees, we won't see this. Volatile basically secures our read and write. So we increment something, and Java will make sure nothing is stored, and we always read from main memory. But volatile, by the way, doesn't guarantee anything else besides I read and write to main memory. That's it, period. Synchronized is basically read and write, the two before, plus we introduce single-thread concurrency or consistency. So we tell Java what you initially assumed about single-thread consistency, please apply this to this piece of code. That's what you have to do. And then we have atomics. And atomics basically ensure that read and writes are encapsulated into a kind of a transaction, so they are safe. So I can count up and count down and do other crazy stuff. This is what an atomic is. And then var handles is basically everything we have seen before in code. So it's basically code that allows you to write programmatically synchronized, volatile, atomic, and access stuff like crazy. Most of you will never ever have to touch a var handle, by the way. This is really for expert library developers. You probably don't want to copy something from Stack Overflow where someone said, use a var handle to fix this problem. So, our toolbox. We have our final. We already discussed this. This is the left one. Now we have to attach final. We have this code in the middle, which is the one that's incorrect because we moved the shared equals local. And on the right side, we basically say, hey, need a fence. So final introduces a fence and says shared local cannot be moved. So neither the computer, the CPU, nor Java will move this piece of code and optimize it. It has to stay this way, which is a little inefficient because I could probably do the store earlier, but I have to wait, otherwise it will be inconsistent. Volatile. There's a nice long definition. The only thing you have to know is I always read from memory, I always write to memory, period. That's it. So if you say, this is volatile and I have to access it, I go to main memory, that's it. If I have to write it, I always write to main memory. I don't keep this in a register for later writing, something like that. This will fix our singleton get instance problem. Because I declare our singleton instance volatile, and now we get plenty of fences included in our code. We have the instance equals null. This is already a fence, so I have to read this from main memory. So I go to main memory and get a state. If the state is null, I go into the synchronize block. Then I read from main memory again. This is important, I read again. And now I might see this is still null. Then I go into my block. We introduce a fence here, so I can't reorder the instance equals local, so I don't expose this too early. And then we leave our synchronization block, and then I do return instance, and I read from main memory again. So this code is basically, I read always from main memory, I write always to main memory. This is way faster than a fully synchronized. You might just attach to get instance, but of course it's slower, because we have to always go to main memory. Therefore, we have these L1, L2, L3 caches. They take care of the problem. If you're lucky, it's in the L1. It's really, really fast. Second lucky, L2. If you have a problem, it might be L3, so it takes 200 nanoseconds or 4 minutes to get to the object. Volatile at work. This is the way it looks like. This is our code. We increment a shared. We have two fences there. The first one prevents that we are reordering anything. The second one makes sure we flush to main memory. And this is the assembler code that will be compiled at the end of the day into your Java program. So the first one, move the data from main memory, increment, move it back to main memory. So not in a register, but just move it back. And then we lock the CPU, or in this case, we lock the stack, and make clear to the CPU, please finish and write back to main memory. Don't do anything else before that, so we don't reorder the code. Really just flush it out. This is our square problem again. So we have the first one, we have a shared that's 0, and we turn this, we keep this the way it is. We know that's a multiplication that's a single one, which by accident is right. So we don't have to do anything. Nobody will do anything because the code works, but the code is wrong. It might not work forever. And the correct one is the volatile one at the end. We read twice from main memory, and then we multiply. The problem is, now we read twice from main memory. Now your square might be actually guaranteed to be not a real square anymore. So correct code, wrong answer. Incorrect code, right answer, by accident. And there's the famous one, synchronized. Synchronized basically builds a nice block where only one thread can enter. And in the beginning, the synchronized says, everything I will use later on, I read from main memory. At the end of the synchronized block, everything I have done will be flushed to main memory. In between, so within the synchronized block, everything I can do, I will do to optimize this code. So it's basically single-thread consistency. I can reorder, I can execute in parallel, stuff like that. As soon as the block ends, I flush it back. And this is how a method call looks like that just increments a single integer without synchronization. So it's just more than one assembler line. And this is synchronization. This is exactly the same code as on the left side, just you added synchronize to it. And this is not everything, so basically it continues for another half of page. And you can see line 21, it might be relatively small, is the only thing we wanted. Everything else is an extra we get because we want to have consistency and single-thread consistency. So memory consistency and single-thread consistency. This is the overhead we get. And what actually Java does at the end of the day, we synchronize the memory, not the thread. So the thread checks the memory, sees the flag, someone is already in this block, and falls asleep. It registers with the operating system to receive an interrupt, and someone else leaves the block, sends an interrupt, the other guy gets woken up, sees that the flag is gone, and continues to run. So Java doesn't synchronize the thread. So not sleep, wake up, things like that. The threads basically synchronize themselves by using the memory consistency we imply here in this case. And therefore, it's really, really hard to change, for instance, in garbage collector implementation, because on the right side, we write to memory a lot. And if a garbage collector in between starts to move objects around because it garbage collects, we have to follow this object to see if this flag is still there. And this is expensive, this takes quite some time, and this makes the implementation of a new garbage collector algorithm kind of really, really difficult. And because we know this synchronization is extremely expensive, Java applies more tricks. This one here has two blocks. I have to enter the first one, leave it, and then enter the second one and leave it. Java says, you know, this is way too expensive. Let's do this. It's absolutely legal. It's the same outcome as before. We can do this. And Java will do it. We'll just basically say, hey, you know, synchronization expensive. Let me get around it, and we get this. If foo is by accident an unsynchronized shared one, an incorrectly synchronized one, by accident it will be synchronized. Other than that, you might just have done something stupid initially, and Java kind of blends this out, and you don't know that this is entirely wrong in the first place, until you basically install a new GDK that slightly changed the implementation, and suddenly you wake up at night because your alert goes off and says, I can't restart the service. This might be the reason. We can also do other things. So for instance, here we have to go into the block, and then we have to leave it, and then we write foo. The thing is, leaving the block is really expensive, and because we block the CPU, because we can't really order anything, we lose basically our execution pipeline automatic concurrency thingy. So what Java does is, you know, let me put this into the synchronization block. Even so you have not two, but only one. This is legal, and this will be done to make your code fly. And it might, once again, lead to synchronization you don't expect. You never see, you are happy with it, until the magic day turns up. Atomics. These are lock-free updates. What is a lock-free update? So we have an atomic here, and we want to increment this. Under the hood, we do this. It's actually Java code. If you look into the GDK implementation of atomic, it really looks this way. So we have a flag that's called applied. We get the variable, we increment this, and then we write it back. While writing it back, we do git. Git in the sense of there's version control on this memory flag. So we basically say, here's the old value, this is the new one. If the old one is still there, write the new one, otherwise tell me. So the computer says, you know, someone was faster, and I basically recalculate the entire loop. So I increment again on the new value, and I also ask the CPU again, hey, memory, just try to write it, and it might say, you know, someone was faster, you have to do this again. The set this and compare it has hardware support. So the CPUs have special support for compare and set operations. We just have to do the state to recycle or to cycle through this loop again, called version control updates, as mentioned before. And the problem is you can wait forever. Nobody ever guarantees that you will finish. You can be stuck in this loop forever. You will probably never be, but you might be. So this is code that's by design not correct. But this never happens, because at some point in time, you are the guy that can actually write to main memory. So this is unsafe code to a certain extent, but it magically works. But you don't have to log anything. This is quite efficient. So more handles, we just jump over this topic because it's way too long. Conclusion, you have to tell Java that something is shared. Otherwise, Java doesn't care at all and might just, compile code that's totally wrong. Or by accident right, you never know. There's no golden rule how your code will be compiled unless you tell Java that you want to have this in a certain way laid out. By the way, Java doesn't manage the cache. The hardware does all the cache management in between CPUs and states and what has been written and what not. Java gives basically hints by using special instructions to block cache lines because we want to write to it, or we block basically the CPU from continuing reordering, stuff like that. This is only what Java does. Everything you do with shared data is not free. Shared data is not free, but shared data can be way faster than immutable. Because immutable has the problem, I have to create memory, or I have to get memory, I have to write to it, then I have to write my data to it, I have to work with it. If you repeat this process, you have basically a lot of memory churn, it could be very expensive. So state management, shared state management might be a way to do it. It depends on your problem. Virtual threads loom, no different story. Everything you heard before applies to virtual threads as well. Because at the end of the day, the virtual thread is nothing else than a thread running on a CPU. It's not a thread on the operating system side. It just basically gets a carrier. But everything you have seen before and heard before about virtual memory handling, stuff like that, still valid. And there is scope values and structured concurrency. That's basically the new language approach, like Go and Rust do it. You get a structure that you don't have to use. But you also get a guarantee, if you use it, that it will be correctly synchronized and you don't run into any of these sharing traps I just laid out before. And this will make probably Venkat very happy. Testing is really hard, but reviewing here is way easier. So if you review code for concurrency problems, that's relatively simple. Testing it, it's close to impossible. That's it. That's the end. Thank you very much.